Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the synchronous motor, and we saw that we can have a wound field synchronous motor or a permanent magnet synchronous motor. So, we will start with discussing the various types of synchronous motor. Now, as we have already seen that we can have a wound field synchronous motor, which can be of two types, a cylindrical rotor, in which the air gap is uniform. So, we have the flux produced by the rotor. So, this is the rotor. So, the windings are placed on the rotor and the air gap is uniform, because the stator is surrounding the rotor is just a cylinder, and hence this is called a cylindrical rotor synchronous motor. On the other hand, in salient pole rotor, the windings are placed around the rotor and we have salient poles like this, protruding poles, and the flux is produced if you apply the Ampere's thumb rule. If the current is flowing into this winding like this, the flux is produced in this particular direction. So, usually cylindrical rotors are used for higher speed application. This is for higher speed, because this can stand higher centrifugal force, and salient pole rotors are used for lower speed application. When the speed is lower, we can go for salient pole structure. Now, the rotor basically produces a DC flux. Unlike an induction motor, here the rotor produces a DC flux, and the DC flux is produced by a DC winding in the rotor. Now, if we replace the physical DC winding by permanent magnet, we get permanent magnet synchronous motor. So, in permanent magnet synchronous motor, we can have various types. One is called a surface mount permanent magnet synchronous motor, and this can have a projecting type or an inset type. In projecting type permanent magnet synchronous motor, what we have here is that the magnets are placed on the surface of the rotor and they are projecting, and they are basically glued by means of epoxy glue. There is a locking arrangement. So, the magnet does not fly off. So, this is basically glued by epoxy glued with some locking arrangement here. So, we have, let us say for a 4 pole structure, we can have north pole, south pole, north pole and south pole, and the permanent magnets cannot be obtained in a single pole. So, we have north pole here and south pole here. So, we have south pole if it is the north pole is below this, and then we have north pole, and then this is the south pole of the permanent magnet, and south pole, and we have north pole. So, this is called the projecting type permanent magnet synchronous motor. And if we go for inset type, the magnet is placed within the rotor, but it is on the surface. So, this is basically placed within the rotor. So, this can be used for little higher speed, because the magnets are not protruding out. And similarly, when we have a permanent magnet, we have north pole and south pole. So, if the north pole is on the surface here, which gives flux in this direction, south pole will be here. Similarly, we have south pole here and north pole here, and north pole and south pole, north pole. So, this is called inset type. The magnets are placed inside the rotor, but on the surface. We have another type of permanent magnet synchronous motor, which are called interior permanent magnet synchronous motor. The magnets are buried within the rotor for better protection. So, in interior permanent magnet, what we have is the following. This is the surface mount. We will have interior. We have interior permanent magnet synchronous motor. Now, in interior permanent magnet synchronous motor, what we have is the following. We have the rotor here, this is the rotor structure, the magnets are placed within this rotor. This is one magnet, the other, and this is how the magnets are placed. So, the magnets are totally within the rotor. So, this is the magnet that we have, and if this is the north pole, this is south pole, this is north and this is south, and since the magnets are within the rotor, it does not basically fly off. So, the interior permanent magnet synchronous motors can be used for higher speed application, and also since the magnets are within the rotor, they are more protected. So, they cannot be demagnetized easily. So, we have some non-magnetic strips here to allow the flux to flow through the air gap. So, this is some non-magnetic strips. So, which will ensure that the flux will come out of this north pole and enter the south pole like this. So, this is the flux path, flux comes out of the north pole and enters the south pole. Similarly, from this the flux will come out of the north pole and enter the south pole, and on the other side also we have the flux paths are like this. So, this is the interior permanent magnet synchronous motors, which are very much popular for electric vehicle application. They are most widely used in electric vehicle applications. Now, with this discussion, let us go back to derive some of the very fundamental equations for synchronous motor. We will first take up a cylindrical rotor synchronous motor, where the field is a cylindrical field and we have winding in the field, and we will be deriving equations for a cylindrical rotor synchronous motor. Cylindrical rotor, wound field synchronous motor. Now, so for simplicity, what we will do here is that we neglect stator losses. So, the equivalent circuit per phase is given as follows. So, what is this equivalent circuit per phase? So, we have neglected the stator losses. So, we have reactance in the stator, which is called the synchronous reactance, and then we have induced EMF, and this is the equivalent circuit. So, this is the field induced EMF, and this we can say as E, and this is the applied voltage, which is V per phase, and this is the stator current, each one is a phasor, and then this is the synchronous reactance JXS. So, we have neglected the resistance part because we have neglected the losses. Now, this E is equal to E angle minus delta. So, for a motor, if we assume that the applied voltage is V angle 0, this is the voltage phasor, the induced EMF lags behind the voltage by an angle delta, because this is a motor operation. So, what we can say here is that the input power is equal to, this is for a single phase. So, if we calculate for 3 phase, we can say 3 V into I s into cos of the angle between them. Theta is the cos of the angle between V and I s, and since we do not have any losses, the power which we get output is P output. So, we have the input power P in, and the power which flows out of this is P out, and that is also same as the mechanical power P m. So, we can say that this power is same as P m, because we have assumed that it is a lossless system. We have ignored the stator losses, there is no core loss here, we can club the friction with the mechanical load. So, P in equal to P out, and that is same as the mechanical output power. Now, we can also draw the phasor diagram for this circuit. Now, when we draw the phasor diagram, we have to write down the vector equation. Now, we have a applied voltage here, and we have the current, and we have the induced EMF. So, by applying KVL, we can write that V is equal to I s x s j I s x s plus E, or we can say that E is equal to V minus j I s x s. So, we can find out the induced EMF by subtracting the drop from the applied voltage. Let us see how we can do that. So, if we say, for example, if we take this as our voltage phasor V, and let us say the current is lagging behind the voltage by an angle. So, this is the I s phasor, and this angle is the current, the power factor angle theta. Now, we have to find out what is the induced EMF. So, this is minus j I s x s. So, if we complete the phasor diagram, this is E, and this angle is delta. So, E is equal to E angle minus delta, because E is lagging behind the voltage by an angle delta. So, what is V? V is applied voltage, that is V angle 0 degree. Now, if this is what we have here, we can write down the expression for I s cos theta. So, or we can find out what is I s. I s is the current which is flowing in the circuit. So, I s is the current which is flowing in the circuit. So, we can write down, or what is I s here? I s is nothing but V minus E by j x s. So, applied voltage minus the induced EMF by the reactance gives us the current phasor. So, the current phasor is nothing but applied voltage minus the induced EMF divided by the reactance. What is applied voltage? Applied voltage is V angle 0. What is the induced EMF? Is E angle minus delta, and this is j x s. So, that is equal to V by x s into angle minus pi by 2 or 90 degree minus E by x s angle minus delta plus pi by 2. Now, here we have a real part and we have an imaginary part. This equation is a complex equation. Our phasor, the reference phasor is this is our reference phasor, this is our reference. So, if we want to find out the real part of this, the real part of this is I s into cos theta is the real part of the I s phasor, and that is equal to V m by x s into cos of pi by 2 minus E by x s into cos of delta plus pi by 2. So, we can simplify this, that is equal to cos pi by 2 is 0 or cos 90 is 0. So, the first term vanishes, the second term cos delta plus 90 is minus sin delta. So, this is E by x s into sin delta. So, this is what we get here. Now, as per our previous equation, what is P output? P output is 3 V into I s cos theta. So, we will be replacing for I s cos theta. So, that is equal to 3 V E by x s into sin delta. So, this gives the mechanical output power of a cylindrical rotor synchronous machine. Now, when we get the mechanical power, we can find out the torque by dividing the mechanical power by the rotor speed. So, what is the rotor speed? The rotor speed is same as the synchronous speed, there is no slip here. So, we can say that the rotor speed is equal to the synchronous speed omega s, because the slip s is equal to 0 for a synchronous machine. So, if the rotor speed is same as the synchronous speed, so what is our torque? Torque is given as the mechanical power by the rotor speed, that is equal to 3 V E sin delta by x s, and we have to divide by the synchronous speed. So, this is what we get here. Now, let us try to understand the equation that gives us the torque. Now, T is equal to 3 V E sin delta by x s by omega m s. Now, V is the applied voltage, which is constant. E is the excitation EMF, the induced EMF, which is constant if the field is kept constant. Now, if we keep the applied voltage constant and if we keep the induced EMF constant, because the speed is a constant speed, the frequency is a constant frequency. So, what we do here, we supply the synchronous motor from a constant voltage, constant frequency source. So, we have a synchronous motor, this is a wound field synchronous motor. So, we supply this motor from a constant frequency, constant voltage source, constant voltage and constant frequency. So, if we do that, the torque is given by T. So, in this case we can plot this torque versus delta. Delta is called the torque angle. So, it means as we go on varying delta, the torque will be changed. The voltage is constant, the field is constant, the frequency is constant, the speed is constant. So, if we want to vary the torque, we can do that by varying the value of delta. So, if we vary the value of delta, we get the torque, various torques here. So, what we get in this case is delta in the x axis and torque in the y axis. So, we get a curve like this. This curve is sin delta. As we change the value of delta, the torque increases. If you increase the value of delta, the torque increases and torque becomes maximum at a value of delta that is equal to pi by 2. So, this is the maximum value of torque. Thereafter, when we increase the torque, delta decreases. So, if you cannot increase the value of torque beyond that. So, if we increase the value of delta, torque will decrease. So, that is the maximum value of torque that we can have. Now, delta can be negative as well, we can extend this in the negative direction as well. So, the negative direction is used usually for braking, for generating. So, this is for motoring, and if you want to brake a synchronous machine, one of the ways to brake is to make torque negative. That means, we have to go for a negative delta. So, the motor will be functioning as a generator in the braking mode. So, this is the braking operation. Now, let us see that we have an advantage, that we have a field winding here. So, field is excited separately by means of a DC source. So, we have Vf and we excite this by means of DC source and to produce a DC flux. Now, we can operate a synchronous motor under various power factor. Induction motor always operates under lagging power factor. However, in a synchronous motor, by controlling the field current, we can operate it in various power factor. It could be lagging, it could be unity power factor, also it could be leading power factor. Let us see the phasor diagram for various power factor conditions. Let us say that we talk about lagging power factor. So, if the power factor is lagging, what we get here is this, that this is applied voltage and the power factor here is lagging here Is. So, we have to find out E here. So, this is minus j Is excess, these are all phasor quantities. So, we get the induced EMF E, which is induced by the field winding, and this is the torque angle, that is delta, and for the motor E lags behind the voltage by an angle delta. So, this is for a lagging power factor. Now, if we make the power factor unity, the voltage and the current will be in phase. So, unity power factor operation, unity power factor. So, if the power factor is made unity, we have the voltage here and we have the current which is in phase, and this is minus j Is excess and this is E, the induced EMF. The power factor here is unity, which means theta angle is 0. So, I and V are in phase and the torque angle is angle between V and E. In this case, E lags behind the voltage V. So, this is corresponding to unity power factor. Similarly, we can make the motor operate in a leading power factor. So, for a leading power factor operation, what we have to do here is that we have to excite the field little more, that is called over excitation. So, this is the voltage V, the power factor here is leading. So, Is leads the voltage by an angle theta, and what about the drop across the reactance? So, we have to see that this makes a 90-degree angle here. So, this is the drop across the reactance. So, this is minus j Is excess, and if we join these 2 points, we get E here, and this angle is delta, the torque angle, and E again lags behind the voltage by an angle delta. Now, what we observe here, that when the value of E is less, we operate in lagging power factor. When the value of E is moderate, we operate close to a unity power factor. When the value of E is more or over excited, we operate in leading power factor. So, that is the advantage of using a wound field synchronous machine, in which we can operate under variable power factor. Now, let us see the torque speed characteristic of a wound field synchronous machine. So, we have already seen that the torque is equal to P m by omega m, that is equal to 3 V e by x s into sin delta. Now, this is for a constant frequency application, constant frequency operation. So, if we plot the torque speed characteristic, this is the speed axis as before, this is the torque axis. Now, the torque is independent of the speed, here the speed is constant. So, the speed is constant and torque is not a function of the speed, it almost remains constant. So, the speed is constant, the speed is constant. So, we have a constant speed motor. So, this is omega m s, the synchronous speed. So, speed here is constant. So, the motor speed is constant here because we are supplying the motor from a constant frequency source. This is not a variable speed operation. So, when we use a synchronous motor from a constant frequency source, the speed of the motor remains constant. So, this is a constant speed motor and the torque actually can either be positive or be negative, as we have already seen that we have possibility that the torque can also be negative. So, this is when the torque is positive we have motoring and torque is negative we have braking, and delta maximum here, this we operate only up to delta equal to pi by 2. So, this is the range of the operation. For braking also we go up to minus pi by 2. So, delta maximum in this case is equal to pi by 2, because after that we have unstable region. So, this is a unstable part and this part is a stable part. So, and this can operate at constant speed, but the maximum torque is T maximum. So, what is T maximum? If we go back, this value is T maximum and it can operate under braking mode and we can operate up to minus T maximum as well, which is corresponding to delta equal to minus pi by 2. So, for delta plus pi by 2 we operate at plus T maximum and delta minus pi by 2 we operate at minus T maximum. So, in this case we have the range of operation here between T maximum and minus T maximum. So, this is the first quadrant. So, we call this to be the motoring operation and this operation in the second quadrant is called the braking operation. So, the speed is constant. So, this is for a fixed frequency supply, motor supplied from a fixed frequency supply. Let us see the analysis of a salient pole synchronous motor. Now, for a salient pole synchronous motor, wound field synchronous motor, we have to draw the equivalent circuit, because here the air gap is non-uniform. We have salient pole in this case, we have one d axis and one quadrature axis. So, the rotor construction is something different. We have the rotor which has salient poles here, and the stator surrounds this structure. So, we have the structure like this. So, this is called the direct axis. And the windings are placed in the rotor like this, and we have the DC voltage which is applied through a slip ring, this is Vf, and the current which flows in the field winding is the If. So, the flux is produced along the pole. So, this is called the direct axis, because the flux is produced along the direct axis. Now, we have an axis which is in between the direct axis, that is called a quadrature axis. So, the axis which is right angle to the direct axis is called the quadrature axis. So, this axis is called the quadrature axis, quadrature axis. So, we can see here that the air gap is less in the direct axis. So, this is our rotor, and stator is the stator inside is a cylinder. So, this is our stator, and here the air gap is less along the direct axis and air gap is more in the quadrature axis. So, we have two synchronous reactances here, one is along the direct axis, the other is along the quadrature axis. The synchronous reactance along the direct axis is called XSD. So, this is XSD. The reactance along the D axis is called XSD. The reactance along the quadrature axis or Q axis, this is called a Q axis, and this is called a D axis. The reactance along the Q axis is called XSQ. So, unlike a cylindrical machine where we have only one synchronous reactance, that is XS, we have two synchronous reactances in a silent pole synchronous machine because of non-uniform air gap. So, we cannot draw a single equivalent circuit for a silent pole synchronous machine. So, we have to take the help of two equivalent circuit, and we have to resolve the MMFs along the D axis and along the Q axis and find out the respective fluxes and calculate the induced EMF. So, we stop here for today's lecture. We will be discussing more about the silent pole synchronous machine in the next lecture.